Okay, so the goal of the meeting is to arrive to sufficient background of this movie. I hope.
Whoa. Ooh, that's what the beginning of the universe was. This is
I'm a big fan of
tree.
that.
This is like when babies watch like little things with like little animals and things bouncing around. Yeah, this is for us.
Yeah.
Oh, to put babies asleep.
Sure.
Mobile.
Well, yeah, but or like it's not
It's
Cocomelon,
like,
but
it's like mental stimulation.
yeah, just like random little things moving around in the babies or like in a tree.
A little bouncing fruit thing.
Yeah, like bouncing fruit or something.
There's a mobile.
No, bro, a mobile is a thing. We're talking
about a show. Like Netflix videos.
No.
Can you tell more? I see excellent analogies, but any other observations?
It looks like the Iron States for sure.
Against states of whom? Of which system? Or like hydrogen like atom. So how would you call this lowest thing?
Us.
So how many p orbitals do you have? And what's like there is a px, py, pz, right? But one can make a transition into p minus p0 and p plus, where this index is magnetic quantum number. So it is our subject, magnetic quantum number. What can you tell about it?
That has a speed. I can remember how the speed.
Okay. But there is magnetic number from it is what Mickey does to other cats or to veterinarian doctors. So Patricia told an important thing. When I'm speaking, I can calmly focus on myself. The word of Patricia was as follows: the magnetic properties, magnetic quantum number associated with spin. Do we applaud to her or say we are not happy? Please join me in criticizing Patricia. So I just repeat her words. She told, I asked, who of you know anything about magnetic quantum number? And she immediately told, magnetic quantum number is related to the spin of electron. Why I'm not 100% happy? This is, well, it is not for record or for the grade, but it is kind of example how well you were performing in your freshman chemistry.
Is it magnetic quantum number is for like how it's oriented?
Good. I will share a recorded freshman chemistry lecture to you together with this one tonight, suggesting that you just review. Thank you so much, Melody. How many quantum numbers hydrogen atom, electron and hydrogen atom has? Exam for freshman chemistry. How many quantum numbers an electronic state in hydrogen atom has?
4.
Okay, what are they? What's the names?
The names, the quantum number.
There are 4 quantum numbers. What are they?
Oh, the spin.
No,
Spin, vibration.
Oh, yeah. Okay.
yeah.
Principal magnetic spin and you doing some natural sciences?
What?
Yeah, he started as a chemistry major here, so he took freshman chemistry with Rogers and stuff.
Principal.
So it's
The angular momentum.
Yes, angular, orbital, L.
L is
L.
momentum.
Okay.
I didn't do very good in chem.
But
Is this
this
like
still can
related to what we're doing versus different?
You see the pictures are upside down the same, right? So the lowest S orbital doesn't rotate at all, right?
Yeah,
Because sphere rotation of sphere is difficult to notice. But if there is a dumbbell, it can rotate in three ways. It can be no rotating along z-axis if it is oriented like a doll, or if it is oriented horizontally, then it can rotate forward or backward. Make sense?
Yeah.
So this two dumbbell thing can rotate forward and backward. Yes, and you see it. Now something is wrong in this figure. They should rotate in the to the left and to the right should rotate in opposite directions. But okay, visual things are not always perfect. So m equals -1, m equals 0, m equals +1. So if we look on this series, the higher the series, the quicker the rotation, right? And in one line, there is a quantum number L that corresponds to how many energy is stored in form of rotation. But rotation, as you were teaching me last time, you were trying first class.
Oh, yeah.
And then, I probably should, when you do it, we'll discover. But then we decided that rotation should be shown this way.
Yes.
Not this one. It's like in a swing.
Like you're tumbling downhill.
Oh well,
Do you not like that one?
well, if it is an infinite rotation without friction, I'll look for the recordings and try to see if the words are applicable.
Oh, okay.
So the higher the L, the quicker is the larger amount of energy stored into rotation. But rotation of these two objects can be like all planets around Sun are rotating in one plane. But no one told that it is a must. One can imagine that some crazy planet will go out of this plane, right?
Yeah.
And it can be rotation in several planes simultaneously. So the additional quantum number that we put on this m axis, and m for Patricia, just m is different from s. So magnetic quantum number and spin quantum number are different. M is magnetism originating from rotation of electron around nuclei, and spin rotation of electron around itself. Okay, so along the m-axis we see how quickly this rotational thing rotates in the xy plane. If you neglect rotation in other planes and move in only one direction, it can have fixed total value of energy stored in rotational degree of freedom, but it can be contributed only from rotation in the xy plane, forward or backward, or it can correspond to rotation out of plane, and then we do not see any movement, right? So nodal planes are in the xy plane if it has this maximal m, and they are perpendicular. They are perpendicular to z, parallel to x and y if rotation is out of xyz plane. Okay. And this is thing that no one is doing this year, but it was one of the projects in previous years, right? So looking how this eigenstate changes over time in magnetic field, but okay.
Dimitri, for the spin quantum number, the positive versus -1/2, does that just mean if it rotates clockwise or counterclockwise?
Yes. But do not tell it in presence of in presence of public. I will.
Okay.
We will have a special lecture for spin, although in true course it should be like half semester on spin. There is a model thinking that electron is like a model, like rotating sphere with a charge smeared on the surface of butter or peanut butter or jelly, and then rotating charge creates magnetic moment, and then this globe can rotate forwards and backwards. This is only a way to get the concept. If one would like to really model it, it will go through nonsense. Like if one chooses a sphere that is equivalent to size of an electron and make it rotating with speed enough to create sufficient magnetic moment, the surface of the sphere should rotate significantly quicker than the speed of light. So it's only an abstract concept telling that intrinsic angular momentum of spin. This you can speak in public.
Okay.
But inside yourself, yes, you should. You may imagine.
Sure.
Like primary school kid goes to geography, takes a globe and spread German. I'm studying. What are you doing? I'm studying spin. Those are for the project, and I think only ever changes kinetic energy, but we all will have a parameter. So if one wants to philosophically summarize all projects into one pattern, we look for response of a certain model, of a certain Hamiltonian, to a change of a parameter. And parameter can be different, like intensity of electric field, or for some distance between things, initial momentum, coupling between X and Y modes, or maybe initial elongation. For melody, it can be, do we excite system once, or we have a sequence of excitations, and for when Fred comes, I'll design a parameter. So it is what, okay, 20 minutes for 2 lectures. What we missed last time? Yeah, come on.
Okay.
So we did transition between different degrees of freedom, and it is a matrix for differential geometry. Now, if we look for momentum along arc lengths, we convert into derivatives over distance and angle. And if we keep on the angle, it has this one over r. And if you plug in the definition of momentum and definition of, Sam surprised me positively that he was knowing cross product from the top of the hand. If you plug it in, the r cancels, and we have the angular momentum operator that has only derivative over angle. Right? Okay. This is an alphabet for description of rotational motion. So recommended to remember it in the middle of the night. And it's simple enough. Now,
For Hirschberger?
he will impress him. I don't know if he will be requesting to memorize equations, but kinetic energy is what? Momentum squared over 2 masses, right? But mathematically, no one will punish me if I multiply and divide fraction on the same number in numerator and denominator, right? It's my frivolous mathematical freedom. So I multiply by r squared, divide by r squared. And then in the numerator, we will have angular momentum squared, because it is like cross product r times p. And in the denominator, we will have mass times r squared, which serves the same role as mass for linear motion. So it's a measure of inertia. If something starts spinning, then it will stay spinning. So angular momentum squared over inertia, right? Or second derivative over angle. So there is no potential. There is only kinetic energy, and kinetic energy for rotational motion is expressed as a second derivative over angle. So we do have Hamiltonian for rotational motion, which is good. You all are experts in Heisenberg equation of motion. We're not going to practice it, but we have this background. So if two operators commute, then they share the same set of eigenstates. And this is a far-going consequence. So we can find, like, if you have angular momentum commuting with Hamiltonian, L squared with Hamiltonian, if you have these properties, then we can find eigenstate of the operator of Z, and then the eigenstates of this operator will be eigenstates of L squared and of Hamiltonian. Make sense? Why? Because it is cheaper, because it is quicker and a shortcut. So here is what we would do together on the blackboard if time allows, but I'll do it here. So first derivative of the unknown wave function in respect to what? Angle, right? Equals to eigenvalue, which will be angular momentum quantum number divided by h bar, times unknown wave function. Can you solve this differential equation?
I could definitely try.
Do you see the answer right away? So probably it is on the next slide, but we have d psi, d phi, and psi. We can d psi equals m d phi, right? These, so log psi, so will be just m phi, which means phi will be t to the power with some constant m, right? You agree? M times phi. And I should use different psi. Yeah. Psi equals e constant m phi. Phi is angle, psi is wave function. And I think the next slide will be the same. So, and there is an imaginary unit that comes from definition of angular momentum operator. And if you take care of this imaginary unit, it will come here. And now you see, maybe you're already thinking about Kilkifis, and you have not enough energy to look at equations, but you may realize that our practices with free space, with Euler and such, were not a waste of time. In rotational motion, we come to the same sort of wave functions as function of angle, looks like a plane wave. Imaginary exponential as function of angle. You see it? So, and m is magnetic quantum number. So, in a free space, motion forwards and backwards means momentum. In the exponential, will be it's p times x. Bigger momentum, larger number of fringes, bigger kinetic energy. Here we look angle wave function is function of angle. Higher m means more fringes, more motion. Positive m, negative m, negative and positive. The same as a particle in the box, we need to implement the boundary conditions. In the particle of the box, at the edges, it was 0. Here, since it is infinitely periodic, we need just to acquire that at angle phi plus 2p, it will be the same as phi. The periodic boundary condition, by the way, when we practice periodic boxes in our Maslach wave packet code, we have the same periodic boundary condition. So disappears and reappears from other side, right? So B, C. Okay, last lecture is finished. Now we are starting today's lecture. One needs to do favorite activity of solution to normalize wave function to find this coefficient C. So wave functions conjugated to itself. So we have rotating in one direction, rotating in counter direction, it will be 1. right? Integrating over for the whole angle will be 2 pi. So therefore the normalization will be 1 over square root of 2 pi. What will be the values of m? When we were studying the particle in the box, we were solving boundary conditions problem. We got general solution and we were looking for particular, right? Particular solution that matches boundary conditions. Same story here. We need to find such values of m so that wave function at incremented angle and original angle will be equal to each other. So if we solve exponential as a product, we can cancel common term in left and right, and then solve the equation 1 equals e to the power I 2 pi m. Right? So for which values of m, this equation will be absolutely correct. So if m equals 0, e to the power 0 is 1. If m equals 1, e to the power I 2 pi I will be again 1. Right? So it's full angle. On a complex plane, x, y, we do, or real imaginary, we do full cycle and we arrive to the same point. So integer number, positive and negative integers will make this equation correct. 0, plus minus 1, plus minus 2, and so forth. We are going much quicker than we should, but this operation is a key, at least for basic quantum theory. So it looks like a little alchemistry or mathematics, but we were solving eigenvalue problem, right? So before we started this slide, we didn't know what are the allowed values of m, and now we do through simple manipulations. So we found infinite number of eigenstates, eigenvalues, and eigenfunctions. Okay, so it looks very simple in this symmetric case, but it is a key problem that one needs to redo for. And this example was selected because it is so simple. For most other cases, it's a lot of more complicated now. Maybe just to prove that one can decompose and solve it independently of time and cosine. But here is the solution. So it is a solution for rotational quantized rotations under 2 approximations. We rotate only in one plane, 2-dimensional rotations, and our rotator is rigid. So our distance between this ions, or distance from electron to ion, doesn't change. Therefore, we have only one independent degree of freedom. Now, interestingly, 0 plus minus 1. If we plug it, I think we saw this little.
Like music?
Do you remember it?
Not this one. I don't remember this music.
Do you remember these images? I think we started the course, like in maybe lecture 2 or 3, we started from this one.
Sure, I think we got rickrolled though.
Yeah, that was, I think, one of them we got rickrolled. I don't remember.
So if those lines are visualization of real and imaginary parts of this function of angle, right? This angle, right? And if the magnetic quantum number has integer value, then the wave comes into itself. If you select the fractional value, then it becomes ugly. And it is a natural law of beauty and ugliness. Beautiful functions are implemented by nature and ugly are defined.
Whoa.
Okay.
Arch world up there.
So now, if we plug in, remember this little trick. I don't know how to remove this panel. Thank you, Kyle. For auto removal. So those are functions. Those are eigenvalues. And this is eigenvalues of the angular momentum operator. But if we formulate Hamiltonian as LZ squared over 2I, then you can find values of energy. and we can just plug in this LZ values, eigenvalues of LZ, and then we'll have the energy is very similar by pattern to what we have for linear motion, like momentum squared over mass, right? So h bar, magnetic quantum number squared over 2I. So here is magnetic quantum number, and on the y it is energy, dimensionless, just to so we keep playing this axis. So if m is 0, nothing is moving. We have just flat function, and it is only one solution. Then we can rotate forwards and backwards, right? So rotation, there are traffic fines, same as for free space. Well, in free space you can move with any velocity. In particle in the box you have only selected energies, right? Same here. One can rotate only with selected values of angular momentum, and one can rotate forwards and backwards. But the energies are the same for forwards and backwards rotation. When there are two states with the same energies, they're called, the word is the same as used for people who do not take care of themselves and degrade intellectually and drink too much.
Is it okay? Let me take a guess here. Is it degenerate?
Yes.
Plus one melody.
Plus one melody. Plus one. So degenerate state, and then if they rotate with quicker magnetic moment, it's another degenerate state. Right? Okay. This is cool. This is correct, but it is rotation only in one plane, right? But in true life, the rotation can go out of plane, and then we can get the. I'm just skipping like 5 lectures. Then we can get the same pattern of answers, analyze them in the same way, but their energies, as there will be two quantum numbers, m and l, orbital and magnetic, and if we plot energy as a function of these quantum numbers, the degeneracy pattern will be different. So our original degeneracy was double degenerate for forward and backward rotation. But if we allow rotations out of plane, there will be additional states. When it rotates in xy plane with lower angular momentum, but it picks up the remaining rotational speed, remaining rotational energy by rotating out of plane. So it rotates out of plane, rotates out of plane, rotates both in plane and out of plane. Make sense? Raise hands if you do not like it. Everyone likes it.
No.
So the energy, instead of before we had m squared, right? Now we have L times L plus 1. So it's almost L squared, but there is a little correction. And this is energy of rotational motion. While magnetic quantum number will tell how much it is contributed by rotation in the xy plane. Now, if you look for eigenstates, remember our little excursion into Patricia's project when we had nodal lines, right? Now, if you do like three-dimensional things, instead of nodal lines, it will be nodal planes or nodal cones, right? And the wave functions for this rigid rotor with three-dimensional rotations will look like isosurfaces, like plus, minus, plus, minus, plus, and nodal cones or nodal planes between them, right? So we need to count nodal planes or number of lobes and nodes. So blue line corresponds to rotation fixed by m, and this theta angle is the remaining rotation. So this motion along theta, I cannot count them, but probably if I do this lobes, nodal 1, 2, 3, 4. So 4 objects and 4 lines. If one goes into increases additional motion along x and y direction, the number of nodal cones will decrease and number of nodal planes in this xy direction will increase. You see, as we go from like north to south pole, we have less nodes. As we go all along the equator, we have more modus bubbles. Right? And here is the maximal angular motion in the xy direction. So nothing changes, no nodal planes as we go from north to the south, and we have a lot, like 6 or whatever, 8 when we go along the equator. This will be like G orbitals, which is never exist in ground state, excited state of uranium, like actinides, just an illustration. And here are these examples. So once again, if this nodal cones going from north to south, it is rotation along the theta angle, motion from north to south. If there are no nodal planes in there, it means rotation along the equator, and they are controlled by different quantum numbers. So here is the thing that we described at the beginning. Okay. Okay. And I know you need to go. You have next class, right? Do you? Do you have next class?
I don't know class like this.
Do you? Anyone has next class?
Technically, yeah, but
Is it cancelled?
yeah.
Okay. Then I'll ask you to stay a couple of minutes more. It will be quick. We are basically done. So there is an interesting observation. So the energies of, and this will be really for Dr. Herberg. So the degeneracy numbers is 1, 3, 5, 7 can be predicted. Now, the energy goes as L times L plus 1. But it is an interesting observation. If you look for transitions between this and this, this and this, this and this, between nearest energies, they will escalate linearly. 2, 4, 6. Okay? So energy offset changes linearly. So one can put it into the table, angular momentum, degeneracy, energy, and offset. And now we can go ahead and predict absorption spectra. Absorption spectra, which go away from the world, of course, are computed by resonance factor that the initial state, final state, must be in resonance with incident light, right? Then there should be non-zero matrix element, and then population factor. Okay. So if you want to predict this wings of an eagle, right?
Whoa.
There are 2 wings, right?
Yeah.
You see that offsets of these lines is linear. It is because there are specific selection rules, so that quantum number of rotations change only by 1, right? And if it changes by 1, I'm going backwards. We have this energy escalation, which is linear, right? So it explains why the feathers of this eagle are equally split. I can try drawing feathers. Well, I'm not a good drawer. Okay? So we see this, but now why they go up and go down? Right? So there are 2 factors. One is the population of each level, and as we go to higher and higher level, it is less and less populated by Mr. Bolson. And the way how the population declines goes like same as in array. Energy divided by 80. And then on one hand, on another, there is degeneracy. So the next higher level lying states will be more and more degenerate. And if we combine factors of resonance condition, thermal population, and degeneracy, we will have this factor that will describe the shape of the wings in the low vibrational spectrum. Okay. Joe was in the class before. It is for dimensions out of. Is it okay if you spend a bit of time on projects?
Yeah, sure.
Today to a project by Patricia. I know it is kind of misuse of the time because she's not enrolled in the class, but we all will enjoy, and later on I think we all will benefit because there are some things. So there are in her project there are static properties and dynamic properties, and connection between them is something really interesting and important. And when it will be her time to present, you can toast how these parts are connected. And now by listening to this little things and related to her, we can get inspiration towards all our projects. So static. I skipped things that she probably will do herself and will organize by introductions, but we have seen the normal modes, right? Eigenstates. Last time I was showing, and it is interesting that one can put nodal lines, right? And one can count them. So here there is one red line, there is one blue line. Here are, I'm going into ascending the energy. Here are the two red lines. Here are one red, one blue. Here are two blues, right? And it looks like plus minus separates. Now with progressive, number of lines should increase. 3 red, 2 red, 1 blue, 2 blue, 1 red, 3 blues. What will be the next? 4 reds, 4 red, 1 blue, 2 red, 2 blue, 1 red, 3 blues, 4 blues, right? And interestingly, one can subtract and add these things. And there are series, this series when these two quantum numbers adding together is giving 4, and subtraction scans from negative to positive. So here are the same eigenstates, right? And one can go into counting the blue lines or counting the red lines. So larger number of nodal lines means larger number of fringes, higher momentum, higher energy, right? And energy can be accumulated either in one or another direction. And in here we have 0 nodal lines, here we have 1 nodal line, here there are 2 nodal lines, here are 3, here are 4, right? So we can reset system of coordinates. Like one system of coordinates is number of nodal lines, and another is subtraction of blue minus red. And this is a pattern that we will get today in our main material of the class when we will be considering rotators with 2 angles. And this is a pattern that you have seen in your refreshment chemistry for orbitals, right? The details are slightly different, but it looks like S, P, D orbitals, right? So this pattern does repeat, and it is a quite standard way that comes out as a solution for Schrödinger equation, if it is symmetric now. So this thing is energy as function of global number of eigenstate, and we see when the number of lines is the same, energies are approximately the same, right? Approximately the same. But since there is an interaction, they are slightly shifted one up, one down. Right? So analysis of static properties is ended in here, but I need to have a connection to dynamic properties that we all run repeatedly. So here is a snapshot of the previous figure with only ground state, first excited and second excited. They first and second excited are approximately equal, but slightly different. They differ by direction where we go. And there is frequency 1, frequency 2, and there is subtraction. So the subtraction of these frequencies of these energies is a critical and most challenging thing that paves a way from static properties to dynamic. We all know several ways to predict the future, that time-dependent solution can be expanded as expansion coefficients of eigenstate, but here the energy offset is most important. So this energy difference defines 1 divided by energy, 1 divided by frequency is a period, and 1 divided by offset of frequencies will be period of energy funneling from this state to this state, energy funneling between different degrees of freedom. I'll stop this subject here, and then we will try to ask these questions in more details from Patricia. And now dynamic properties. So one creates the initial position a little bit elongated from the equilibrium, and one initially starts where only one x mode is elongated, and y doesn't have any motion. But as time passes by, you see this horizontal motion converts into vertical. Right, the center of wave packet does different shapes, different trajectories, and through following this trajectory, it draws a path in the middle. By looking at this path, we see how energy funnels between different modes. So here is this little thing, right? And one can decompose it on motion in x and y direction. So in one direction, it starts with maximum amplitude, and then it decreases to 0. In another one, it starts from 0 and then ramps up. If one looks on this thing and subtract and adds and subtracts them, then one will come to 2 eigenmodes, 2 normal modes that do not change their amplitude. And they have slightly different frequencies, slightly different periods. If you look for the whole thing, during this panel, the red one does 12 oscillations and blue one does 13. And depending on their offset, there is a musical thing. Does any of you play guitar? Does any of you tune piano? You miss a lot.
Does tuning my violin count?
Huh?
Just tuning our violin.
Yes, absolutely. Melody, do you do it?
Occasionally.
Okay. So here is a Wikipedia thing on this tuning, and if you go there, I just really want to go to this link that I promise we all will enjoy. We will enjoy.
Each phenomenon.
Yes. Control click to hold.
More video?
No.
Oh.
Well, some video, but video is not as big fun as this little thing.
Sound. Yeah, I like that.
So this is a
That tickles my brain.
scientific sound. So there are the whole sound clip is 6 seconds long, and it's chopped on 3 periods. So first shows blue wave, red wave, and then their superposition. So let's listen to it. So one tone, second tone, and then when they are together, what do you hear?
It's
So
like
fluctuating the intensity. So we add together 2 waves of the same amplitude with slightly different frequency, and their superposition gives fluctuations of intensity. So this phenomenon is called beats. It is, yeah, yes. And some people do have absolute musical ear and they can tune musical instruments easily. But even a person without any musical talent can tune string instrument. So if there is a how do you call it? Fork, tuning fork, and a string. So if they are absolutely identical in frequency, then you'll hear the same tone. But if they are off, you will hear the beats, and you do not need to be musical. You just identify intensity and change. And by elongating or contracting string more or less, one can change how often the beats will come. And one can come to the period of beats will be absolutely infinite, which means they are absolutely tuned. Right? And here in Patricia's project, we do see, if you scroll back, we do see the same thing. So there are two normal modes, two eigenstates, and when they superimpose, there is a transition from some rotation. But meeting is done. Meeting is done. Oh, thank you, Melody.
Oh, yeah.
Woo! Congratulations. Happy Thanksgiving. Relax, refresh. If you want to invest some electronics, email me. I will be answering. But looking forward to see you in a week.
Yeah.